We were in the process of calculating the band structure of silicon. Maybe 2 lectures ago, we calculated all these matrix elements, like V SS sigma, V SP sigma, V PP sigma, V PP pi. And then we went on to just define the geometric structure of this crystal, what the lattice vectors are, which you see here, where the nearest neighbors are. And then we define these, our block sum basis, as we're going to do every time we do a problem. Like this is a recipe. You define your localized orbital basis. From your localized orbital basis, you construct your block sum basis, one for each type of localized orbital on each type of atom. So we got one S and 3 P's on the A atom, one S and 3 P's on the B atom. And then once you've defined that, you go ahead and you calculate your matrix elements in this block sum basis. And the only way to do that is to expand out these definitions back in terms of their sum over the lattice vectors R. These are your 4 nearest neighbors. So for any A atom, it has these 4 nearest neighbors to the B atoms. And since we're doing a nearest neighbor model, those, when you do your off-diagonal matrix elements, those will be your 4 matrix elements that you need to sum up, which is what we did last time. And so we worked through this for various matrix elements, SS, SP, various types of SP, and the various types of PP matrix elements, like PX to PX and PX to PY, etc. And we notice that a lot of these, so these 4 terms here and these 4 phase factors come from that sum over the 4 nearest neighbors. And we notice that in many of these off-diagonal matrix elements between S and P, or even between P and P, you get 2 positive signs and 2 negative signs in front of these phase factors. So when K equals 0, all those matrix elements are going to disappear, i.e. at the gamma point, and your Hamiltonian matrix will become very simple at the gamma point. But you notice, so the only ones that aren't going to disappear are the ones between S and S, and the ones, if you look at this matrix element between X, PX, and PX, that's not going to disappear because it's all positive. And same for PY, PY, PZ, and PZ. And so this Hamiltonian is going to decouple into a very simple form at K equals 0. I guess we wrote down, and I guess that's as far as we got. So the only thing we haven't done so far is calculate. So these are all the off-diagonal matrix elements. The only thing we haven't done so far is calculate the diagonal matrix elements, which are very simple. They're just going to give you the on-site energies, as always in a nearest neighbor model. First we'll just do the diagonal elements, and then go ahead and construct the 8x8 Hamiltonian and look at it for K equal to 0 and maybe K equal X. Or maybe that's a homework problem, I can't remember. Okay, so the only thing we have not done are the diagonal matrix elements. So if we look at, and I guess I thought they were so easy I don't even see them in my notes. So let me just, so this is the diagonal elements. So for example, we'll look at something like S, A, K. Right? That's what we mean by the diagonal matrix. It's a matrix element between an orbital and itself. So the S orbital on the A atom and the S orbital on the A atom, or a PX orbital on the A atom and a PX on the A, etc. You do the usual thing. You expand that out as its double sum. That's 1 over n sum R1 sum R2, since they're both on the A atom, S A R1 H S A R2 e to the I K dot R2 minus R1, right? Because the S the S with the R1, this is the one that's complex conjugated, so that's why you get the negative sign there, right?
How exactly do you write the notation for the K? Are you writing that as a subscript, or are you writing that as like?
Just like I write the R here, right?
Okay, so it's just right next to it.
Yeah.
But the A is a subscript, correct?
A is a subscript, because you can have an S on the A or an S on the B. It doesn't have to be, as long as your notation just uniquely defines what orbital and what K you're talking about. I could just line them all up in there with commas, for example. You just need to uniquely identify what orbital, what atom, and what K or what R you're talking about. And later we can throw a spin in there too, an up or down. All right, so, well, this is the nearest neighbor model, and we know that the A atom, the nearest neighbors of the A atom are all B atoms, so none of the nearest neighbors are going to be another A atom. So the only matrix element in this double sum, so as usual, we'll fix R1 at the origin, right? You fix R1 at the origin, you do your sum over R2, and the only non-zero matrix element you're going to get is when R1 equals R2, when they're the same. And the matrix element is just going to, we're just going to call this the energy of the s orbital, epsilon sub s, on the A atom. And I guess, you know, if we were doing gallium arsenide, so the A atom and the B atom would have different, right, s orbital energies, like what we talked about for different ionization potentials, for example. But for silicon, they'd be the same. And if you go through the same exercise with any p orbital, you get the same thing happens if we do, let's choose one, xa, k, h, x, a, k. That's just going to give you epsilon p a. That's it. Right. So this Kronecker delta function will collapse, say, the sum over R2 and then the sum over R1. It also then kills off my phase factor, right? If you set R1 equal to R2. And then the sum over R1 just kills off the 1 over n. So finally, this is just equal to epsilon. The whole thing is just epsilon S A. A P1 would be epsilon PA, and the important thing is that if I do it for, say, the PY orbital, that's also epsilon PA, because all the P orbitals have the same on-site energy. Just because it's PX, PY, or PZ, they all have the same on-site energy the way we set this up. And all P orbitals have the same on-site energy. And yeah, I mean, I guess you may run into, people talk about crystal field splitting. I don't know if anyone has seen that concept. But due to symmetry, you could have situations where, say, a PZ orbital sees a different, something different than the PX and PY orbitals due to, say, the crystal is like, it's not cubic. It could have like a long axis and, in-plane lattice vector, and then maybe a longer C lattice vector, and then the PZ orbital would see something different, and so its on-site energy would be different than the PX and PY. But for these cubic semiconductors, everything looks the same in all directions. X, Y, and Z are equivalent. And so all the P orbitals have the same on-site energy for a given atom. And so these will be our diagonal elements. Same deal for the, we look at the B atom, and any of the PX, PY, PZ will be just epsilon P, B. So in this nearest neighbor model, as you've seen before, there's no K dependence to the diagonal matrix elements, only the off-diagonal matrix elements. Again, because the diagonal ones only have matrix elements with themselves in this nearest neighbor approximation, which kills off that phase factor. Okay, so now we're ready to write down the general form of our Hamiltonian. Okay, leave some space. This is an 8 by 8 matrix. And the way we're going to order this in terms of atom and matrix elements, so in the same order goes up here. So all these guys are on the A atom, and all these guys are on the B atom. Okay. So that's going to be the way we order. And the order is, completely arbitrary and up to you, as long as you keep the order once you decide what it is. So that, the way you set up your column order is going to be the way you set up your row order. And then you just, the diagonal elements are easy. We just said what they are. So this first block will be between the matrix elements between, the A atom orbitals and themselves. So this is all, the upper left block is all A orbitals. So this is just our epsilon SA, epsilon PA, ditto, and ditto. And everything else is 0 in here. So the diagonal blocks are diagonal in this nearest neighbor model until we include spin orbit coupling, then they won't be anymore. But for now, they're diagonal. And these will be epsilon B. This is the only difference. Epsilon B, sorry, I'm getting it backwards. Epsilon, SB. So epsilon sub S, superscript B, epsilon sub P, superscript B, P, superscript B, and epsilon sub P, superscript B, and everything else up here. And this block is also 0. So the diagonal blocks are themselves diagonal. And then the only question, also all the interesting stuff is happening in the off-diagonal blocks, is coupling the A atom to the B atom. And so I'm just going to symbolically write, this is going to have a lot of elements that are going to be K dependent. So I'll just say that this is our VAB, which is a function of K. And in general, it will be completely filled. There'll be matrix elements at an arbitrary K in every term there. All 4 by 4 elements will have something there in general for an arbitrary K. And of course, this block has to just be this same matrix, Hermitian conjugate. So I'll write it like this: A comma B as a function of K. And this is, so whatever that matrix was in that upper corner, we just do the Hermitian conjugate, right? Which is the conjugate transpose, right? So whatever this the 4 by 4 matrix was up here, you do the transpose conjugate, and you put it down in the other lower block, right? That's the way every Hamiltonian must be, because it's Hermitian, right? So that's going to be the general form of your 8 by 8. And, if you think about it, it's just an extension of what you've been doing for, your polyacetylene, your graphene. There it was 2 by 2. Your diagonal block was just, some number, epsilon. Your off diagonal we call T of K. And now these have turned into matrices. Right? It's not just a scalar, it's not a number anymore. But they're matrices, but the form is like exactly the same as what you had for polyacetylene or graphene in the pi bond model. And so, there's only, unless this Hamiltonian simplifies considerably, your only option is to just, for each K you fill in whatever that V matrix is, and you send it off to MATLAB or whatever your favorite eigensolver program is. You do get the eigenenergies at each K. You'll get 8 of them because it's 8 by 8. And then you just, at each K, you plot your 8 energies. You move along your K axis, plot your 8 energies, and you'll generate your 8 bands for silicon or gallium arsenide or whatever it is you're trying to model. So that's the way you do it numerically, but now let's look at some special k points like k equals 0 that I've been mentioning. Okay, so we're going to look at the form of this Hamiltonian in k equals 0, which is the gamma point. It's the gamma point in the Brillouin zone. So that, as we've been pointing out, the diagonal elements don't change because they're not functions of k. But the off-diagonal, so we're going to look at the off-diagonal matrix elements and evaluate them at k equal to 0. Okay, so, well, we'll start with the S state. So we have SA, k equal to 0, H, SB, k equal to 0. And that is just equal to V, SS sigma. And as you know, when k equals 0, all these phase factors are just plus or minus 1, but this didn't have any change in sign, so all your phase factors just become 1. All right, so that's just 4 SS sigma. And this is defined, I think, in Slater-Coster paper as simply V S S. Okay, so this defines the variable VSS. Well, let's look at an S, SA, k equals 0, H, not S, sorry, P, X, XB, k equals 0. And that was equal to 1 over root 3 VSS sigma, or P sigma, times the sum of the phase factors, but 2 had a positive sign, 2 had a negative sign. So k equal to 0, that's just equal to 0. And all those matrix elements between the s and the p orbitals disappear. And that's going to be the same for, that's also the same for SA, YB. So there are no matrix elements between the s and the p orbitals at k equal to 0. And there's actually, let's see, the only non-zero matrix elements are the one we just did for s and s. The only other ones where you didn't have this alternating plus and minus sign in the phase factors was between px, px, py, py, and pz, pz. So I guess we had 1/3 of the thing in the brackets times the 4 phase factors, but they're all positive, and that gives me the factor of 4 out front. And again, this is defined as simply Vxx. So this is something you'll see if you look at parameters in the literature. Some people may give you Vxx, or what was the other one I said? VSS, and you just need to understand what these things are. And this is how they're defined in terms of this VPP sigma and VPP pi. And this is exactly the same that you're going to get for PY, PY, and PZ, PZ. Okay, and these are our 4 non-zero matrix elements: SS, XX, YY, and ZZ. That's all there is. Everything else is 0. So just, for example, XA for a different type of p orbital, like x to y, that's 0 at k equal to 0. Or if I replace y with z, that's 0. Okay, so there's 4 non-zero matrix elements. So what we're going to do is reorder the way we write down the elements in our matrix, so it becomes obvious what's going on, and we can actually solve this 8 by 8 matrix analytically. Okay, so again, I need an 8 by 8 matrix here. And now I'm going to order them like this, SB. So what I'm going to do is order them in a way so that all the elements that have a matrix element between them, I'm ordering next to each other. So XA, XB, YA, and YB, and ZA, and ZB. And you got to do the same ordering across the top. Okay, so that's how I'm going to order my matrix, and then I just write down the non-zero matrix elements. An s orbital has no other matrix elements, so these are all 0. And now we do the p orbital. So, well, the diagonal element is just epsilon p a, and the other diagonal is epsilon pb. And their matrix element between two p orbitals was Vxx, and everything else is 0. And the same for the py orbitals, and finally the pz orbitals. Okay, and what you see is that this is broken up into a block, what's called a block diagonal form. So, where you have these two by two blocks. And when you have this block diagonal form, it means you can treat each block, each 2 by 2 block all by itself and ignore everything else because there's no coupling between the blocks. There is no coupling between the blocks. So you can diagonalize each block all by itself. If you think of, this becomes your eigenvalue problem. The eigenvalue of, say, block 1, this upper left diagonal block, is just going to have the form of, C1, C2, and then all zeros. And then, the next, so in the next block, it would be, 2 zeros, and then, C3, C4, and then all zeros. So each block is going to be diagonalized just independently of the others whenever your Hamiltonian becomes block diagonal like this. And so now we're going to simplify it even more and say, let's consider silicon and germanium. And the reason is because then we get one more simplification, that these diagonal energies become the same. So epsilon SA, am I doing it backwards? Yeah, sorry. Epsilon SA is going to equal epsilon SB because it's the same type of atom. And epsilon PA is epsilon PB. And things become really simple. Okay?
Is the general rule? Or
What's that?
is it the general rule? Or it happens for silicon?
And germanium, because both atoms are identical.
For example, graphene or whatever.
Graphene, yeah, also true. Both atoms are identical. So you've got 2 atoms in your unit cell, primitive cell, right? And they're both silicon, for example, for silicon.
Oh, so they're both silicon.
As opposed to gallium arsenide, where one would be gallium, the other would be arsenic.
Oh, okay, so consider just
Yeah,
silicon.
so
consider
either silicon or germanium. I'm not talking about an alloy or something.
Okay.
But so the crystal structure we're doing is generic for all of these crystals: silicon, germanium, and a bunch of 3,5s like gallium arsenide, indium arsenide, indium phosphide, et cetera, et cetera. So the 3,5s, the 2 atoms are different, so these diagonal energies would be different. But for silicon and germanium, they're the same, so they become the same. That's all. Okay, so if that's true, then we can just look at, and then it becomes real simple. If we look at this first block, just for the S states, well, you're going to get it's a 2 by 2 block, right? So you're going to get 2 eigenenergies. You all know 2 by 2 matrices by now. It's a 2 by 2 block, so for that S state, the 2 S states, you're going to get 2 energies. And for the P states, Well, you've got 3 2x2 blocks, but each of those 3 are identical. They're all the same. If we go back and look, right, the p states, we've got 3 blocks for the p states, but each one of these blocks is exactly the same as the other block. So we've got 3 blocks, but they're all identical, which means these energies are going to be 3-fold degenerate for the p states. And so we'll get also 2 eigenenergies for the p states, but they're going to be 3-fold degenerate. So again, you're thinking of a 2x2 matrix, you're going to get, the upper energy, the lower energy, and for each one of those, you'll have 3 states. So we're going to have 2 energies coming from the s states, and they're just going to be epsilon s plus or minus VSS, and the p energies are just epsilon p plus or minus VXX. Those are the energies you're going to get. Okay, and if we first look at silicon. So for silicon, all we've looked at right now is just at K equal to 0. If you look at the full band structure, I'll look at beyond K equals 0 and then focus in on K equals 0. Again, this is without spin orbit coupling. You're going to have your 3 states corresponding to your valence band. Way down here, you're going to have the bonding s orbital, and there's really 3 states right here. One line is on top of another. Up here, you've got your conduction bands, like something like this. Your lowest conduction bands. This is the s antibonding orbital up here. This is a p antibonding orbital, and down here you have your p bonding orbitals, and here your s bonding orbital. And if we draw one of these energy splitting diagrams, it shows what happens when you bring your atoms close together. We start off with our s state, epsilon s, and epsilon p, and then we bring the atoms close together to turn on this off-diagonal coupling, and the p splits like this, and each one of these levels is 3-fold degenerate. Okay, each one of those levels is 3-fold degenerate, and the s splits like this, and this is your s bonding, p bonding, your p antibonding, and s antibonding. So for a direct gap, I mean, it just depends on the matrix elements. For a direct gap material, you would generally have a situation where the conduction band edge is made out of the s orbitals. So for a direct gap material, this is your valence band. This is your valence band edge here, these 3 guys. And for a direct gap material, you'd have this s antibonding state right in here, and then this would be your band gap for like gallium arsenide. But for silicon, that gets pushed up above the p antibonding states, and it's just a matter of the strength of the various matrix elements and how these levels get ordered finally. So for gallium arsenide, you would have, let's choose another color. For gallium arsenide, you'd have your S antibonding coming off there instead of way up here, and then you would have a direct gap material. For germanium, it's slightly different, and it's just sort of, I don't have any deep fundamental explanation because the crystal structures are identical, right? It's just the magnitudes of the matrix elements change a little bit. So for germanium, we have, if I do the sort of schematic of the entire band structure first, what do we got? So the valence band always looks pretty much the same. You've got your light hole and heavy hole band coming off here. So 2 light holes, a heavy hole. Well, one of them will become our split-off band, so we don't have to get too worried about them right now. When we turn on spin-orbit coupling, you'll break some of that degeneracy. You still have your S anti-bonding level way down here. And then what's different is in the conduction band, you've got your P anti-bonding up here, which comes down like this, and then your S kind of crosses and does something like this. So this is your S anti-bonding, P anti-bonding, P bonding, and S bonding orbitals. And if we draw this sort of level splitting type picture, which is just valid right at k equal to 0, we start off with our energy of the S orbital, the energy of the P orbital, and we bring the atoms together. This guy will do its thing and split, and each one will be threefold degenerate. And then for germanium, at the K point, at the gamma point, sorry, at K equal to 0, this guy will do what we just talked about, end up right in between the P bonding and P anti-bonding states. And then you'll have this lower level that really doesn't concern us for electronics way down here. So again, this is your S bonding, P bonding, your S anti-bonding, and P anti-bonding. And that's how they align up right at gamma. So again, this is germanium at the gamma point. And if you look at this, you'd think, oh, this must be a direct gap material. But actually it's not, because this P anti-bond, this band that starts off as your P anti-bonding band actually becomes the band minimum out at out along the 111 point of the Brillouin zone, and it will actually give slightly below that S orbital anti-bonding band at gamma by about 150 millivolts. So they say germanium is nearly direct, but the band minimum is actually at the L point. Sorry, this is the L point of your Brillouin zone. And that point is about 150 millivolts below the band edge at the gamma point. So it's not quite direct. But it's a lot more direct than silicon. Again, this is silicon at gamma. Okay, so that's the story of silicon or germanium at k equals 0 at the gamma point without spin-orbit coupling. This is how your states break up. As we said when we did the two-band model, the valence band is completely p-type. Remember, the simple two-band model I said is a caricature of the real deal. And now we see that indeed the valence band at gamma at the k point is completely p-type. It's completely composed of p orbitals. And not only that, each one of the states, well, until you turn on spin-orbit coupling, is pure px, pure py, or pure pz. Even the p orbitals aren't talking to each other at gamma. And the conduction band, at least for the direct gap materials, is a pure S state. And so you go something that looks a little more direct, or germanium. So the conduction band at gamma so this would be your E sub C at gamma, right? It's not really your true conduction band. At the gamma point, it's your lowest band. Would be composed purely of S orbitals, anti-bonding S orbitals, equally shared on each atom, exactly like what you did for that two-band model. So once we've done this, I guess, just like you did for we worried about for the simple models, where the question now would be, how do you know where the Fermi level is? Well, what you do, it's just a matter of counting. You fill up your states with 8 electrons, because you got 2 atoms, 4 in each valence shell, so 8 total. We need to put them somewhere, and you put 2 atoms. 2 electrons, 1 up spin, 1 down spin in each energy level, starting from the bottom, of course. And when you've counted, so we've got up 2 here, and you're going to have, they're so close together, 6 here, and that's 8, and this probably isn't the proper spin configuration. That's not my concern at the moment. And so that accounts for your 8 electrons. And so that means that if you were to draw your Fermi level, you draw it in between here, and that's also tells you where your band gap is, at least at the gamma point for a direct gap material. Right? You just count your 8 electrons, put 2 in each level, and that tells you where the Fermi level is. Any questions so far? Because that was the easy part. Now we're going to do spin orbit coupling. That's when things get complicated. I think when you finally finish like 2 sets of graphing homework, you're going to calculate what this Hamiltonian looks like at the x point. I did gamma. I did the easy problem. You'll get to calculate what this 8 by 8 Hamiltonian looks like at the x point and see how it decouples at the x point. So that's just taking all your matrix elements. Don't freak out. Setting k equal to pi over a, right? And seeing what disappears, and reordering your Hamiltonian so that you can do something analytically. That's it. And then now to go further, to get the valence band better and understand why you just have a light hole, a heavy hole, and a split off band. You really don't have 3 degenerate bands right there in your valence band. You need to understand spin orbit coupling. And that takes a while. We have to start talking seriously about spin for the first time. Okay, so until now we've ignored electron spin altogether, except when we filled up the energy levels, and we could put like 2 electrons in each level because we knew that there'd be an upspin and a downspin. So for each of so this is going to affect our basis states. The size of our basis is going to have to double, because before we just had, say, for a single A atom, we had S, Px, Py, Pz, and now for each one of those, we've got to have an upspin and a downspin. So our 8 by 8 matrix now becomes 16 by 16. So first thing is how this affects our basis. So for each of our orbital states, there are 2 spin states, which we'll represent in the usual way, just up and down. And so your basis states double, and if there were no spin orbit coupling, then this would just be a trivial sort of doubling of your Hamiltonian, because just like we saw at k equals 0, if there's no matrix element between 2 states, you can diagonalize them separately, and if there's no spin orbit coupling, there's no matrix element between any upspin or any downspin, and so you just double your Hamiltonian, and the upspins live in their own world, the downspins live in their own world. You just do exactly what we've done so far. Okay, so what is this spin orbit coupling Hamiltonian? Well, the way we're going to write it is this. So lambda will be a coupling strength, which we'll say a little bit about. It becomes an empirical parameter eventually to fit the right spin orbit splitting of your band structure. Okay, so this HSO is going to be our spin orbit Hamiltonian, and L will be your orbital angular momentum. S is your spin angular momentum. This would be your operator. All right, so the operators for orbital and spin angular momentum, L and S. And this spin orbit Hamiltonian is just proportional to the dot product between the two. But the L is going to act on the orbital degree of freedom. S is going to act on the spin degree of freedom. our total Hamiltonian, we're going to write as H. It's going to equal to H sub TB, which stands for tight binding. So this is the Hamiltonian we've been looking at up till now. Our tight binding, nearest neighbor tight binding Hamiltonian. That's that thing. We just did it. That's our 8 by 8. So we know everything about that so far. Plus, we have to add this extra guy on now, which is going to give us some new matrix elements we'll have to figure out and then see what they do to the wave functions and eigenstates and all that. You know, what's the physics behind spin-orbit coupling? Sort of the cartoon physics is this. You've got your electron, and in this sort of solar system picture of an atom, your electron has some angular momentum. You can think of it as, say, going around in a circle around the nucleus. So if we'll say that's supposed to be a circle, sorry. So if we say this is the velocity, here's our little electron. It has some spin. It has charge, which is negative. And so the current, because the charge is negative, it's going in the opposite direction from the velocity, right? Current is charge times velocity. Since the charge is negative, that's current is the opposite direction. And so if you have charge going around in a circle by, sorry, I've forgotten my electromagnetic laws. It's like, which law is this? Probably all of them are saying Ampere, Biot-Savart, whatever. This gives rise to a magnetic field. A current loop gives rise to a magnetic field. Right? A current loop gives rise to a magnetic field. Right? Your right-hand rule and all that. Put your thumb in the direction of current. And that's how you get the direction of the magnetic field. You put your thumb in the direction of J, and your fingers point in the direction of the magnetic field. Freshman physics. Okay, so this current is going around, your electron going around in a circle, and that's your orbital. So this is due, this current is due to your, due to the orbital angular momentum. It's related to the orbital angular momentum, L. Well, if you have a magnetic field, then the energy, the magnetic field and the spin, they interact by H. So if you just have a spin in a magnetic field, that spin wants to, well, depending on the sign of mu, which I don't need to get into right now. Let's say mu is positive. So if mu is positive, then that electron, what's it going to want to do? If mu is negative. Okay, if mu is negative, then the electron will lower its energy by being aligned with the spin, right? So if the spin is, if the spin is aligned with the magnetic field and mu is negative, then it will be in a lower energy state than if it's anti-aligned with the magnetic field, right? If B dot S is +1, then some negative mu times +1 will be a lower energy than the opposite spin. And so this gives rise to spin splitting, right, when you have spin in the presence of a magnetic field. And this magnetic field is being generated by the orbital angular momentum and the fact that the electron is a charged particle. And so this gives rise to this interaction between the orbital angular momentum and the spin. And that's your spin-orbit coupling. And now we're going to spend a considerable amount of time figuring out how to calculate the matrix elements of this new Hamiltonian HSO. And to do that, we're going to have to do a transformation of basis from what you would want to write down. So initially, what you would want to do, or what you would do naturally, is to just take your old basis, and everywhere you had, say, SA before, now you just double it with an up and a down. Right? That's how you would include spin. And the same for all the other orbitals that we had, XA up, XA down. Right, so for every one of our prior orbitals in our 8 orbital basis, we just double it, making it 1 up and 1 down spin. That would be the first thing you do. But these are what's called mixed states. They're not eigenfunctions of the total angular momentum. So J is a total angular momentum. And the way we are going to, sort of the procedure we're going to do to evaluate these matrix elements are to do a change of basis so that our new basis will be what they call pure angular momentum states. There'll be eigenfunctions of the pure angular momentum operator J, and go from there. So let's start that process. We'll just begin it and continue next time. Okay, so the total angular momentum is related to L and S like this. So the magnitude J squared is equal to L plus S squared. It's actually, yeah, that's correct. And so if I write out what that means, you know, you do magnitude, I'm being a little sloppy, so magnitude squared. So the squared means magnitude squared. And to get magnitude squared of any vector, you just do like, you know, take the dot product with itself. And so if I take the dot product of L plus S with itself, I'm going to get L squared plus S squared plus 2L dot S. Right? So this is J squared. So this is the relationship between the total angular momentum and L and S. And if you notice, this last term here is our, you know, proportional to our HSO. That's the thing we need the matrix element of. And so we can move the other terms to the left-hand side and solve for HSO in terms, and this L dot S in terms of J squared, L squared, and S squared. And that's what we're going to do. And so L dot S, which is what we really need, because we have to calculate the matrix elements of this L dot S, is equal to 1/2 J squared minus L squared minus S squared. So we'll actually be calculating the matrix elements of the right-hand side of that to get the matrix elements of L dot S. And I think that's enough for this time. We'll review this next time and go on from there.